So previously, I've hinted at this continuity equation, and I've hinted at how we're interested in following the concentration of electrons and holes as a function of location and time. So in order to derive this continuity equation, we need to account for every process that affects electron and hole concentration. And so far we've covered drift current, let's call that JD. We've covered diffusion current, JDiff. And now we're going to cover recombination and generation. And these two are sort of the last two mechanisms that we need in order to derive our continuity equation and actually start solving real world problems. So in this video, we're going to talk about recombination and generation. So remember how I said at temperature equals 0 Kelvin, we've got all these silicon atoms bonded to each other. And none of the electrons are in the conduction band. None of the electrons are broken bonds and are free to move around. They're all constrained to the silicon lattice. So at T equals 0 degrees Kelvin, all the electrons are constrained to the silicon lattice. But then as we start to increase the temperature, the system starts getting available energy. And some of these electrons have enough energy to jump and break their bond and leave behind a hole. And we call that H+. Because it's a positively charged, effectively it acts like a positively charged particle. And so this is at T greater than 0 degrees Kelvin. This process is known as generation. And that's just because it's literally the generation of electron-hole pairs just from thermal processes. Now, you don't have to just have thermal generation. You can have other processes that cause generation. For example, if we shine light on this semiconductor, so we shine photons of a certain energy, if those photons have enough energy to break one of these silicon bonds, so say one of these photons interacts with one of these electrons and the electron is able to break its bond, has enough energy to break its bond, then the electron will do so and it'll leave behind a hole. So in terms of generation, there's two dominant mechanisms, or really three dominant mechanisms that we're going to talk about. The first is under the category of thermal generation. And under thermal generation, there's direct thermal generation and indirect. Or RG center generation. And the direct thermal generation is just if we've got our conduction band and our valence band, it's just an electron being excited directly up from the valence band to the conduction band and leaving behind a hole. Nothing fancy. In indirect thermal generation, however, we've got a slightly different process. So we've got our conduction band up here, we've got our valence band, but it turns out that due to imperfections in the silicon lattice, there are some states available in the center of the band gap where there aren't supposed to be any states. Not many, but there are some. And there's enough for these electrons to hop up into these states sort of as an intermediate way station and then hop up to the conduction band and leaving behind a hole in the valence band. So this is called RG center or indirect thermal generation. Now, if you imagine that these generation, there's a third major mechanism of generation. So we'll call this the first mechanism, the second mechanism. There's a third major mechanism, and that's light, which I previously discussed very briefly. So if you have photons of sufficient energy, then the photons can excite the electrons directly from the valence band to the conduction band. Now, if you imagine that this generation process just keeps taking place and keeps taking place, we're going to get more and more bonds broken in our silicon lattice. So we're going to have electrons split off from this one. We're going to have electrons split off from here, electrons split off from here, electrons split off from here. And eventually we're going to have no bonds left, and we're going to have nothing but electrons and holes. But we know that silicon, if we just leave it in a room, we know that it doesn't just spontaneously melt and all its bonds and structure dissolves. So there has to be a mechanism of getting rid of these excessive electrons and holes. And that mechanism is called recombination. So imagine if I've got just a couple electrons and a couple holes, and they're confined to this extremely large silicon block, then they're not going to see each other very often. But if I start to get more and more holes and more electrons, then the chance that the electrons and the holes will actually meet each other becomes greater and greater. And this is specifically free electrons and free holes, or free electrons and holes. So at some point, when we get too many electrons and holes, they're going to start recombining quite quickly. So these electron hole pairs are going to meet, and then they're going to be annihilated. And in doing so, they're going to give off a photon, HF, or H nu if you prefer. And then they're just going to disappear. So they're no longer in the semiconductor. The electron returned to the valence band, and the hole returned to the conduction band. Neither of them can conduct electricity anymore. And so at a certain point, this process reaches a steady state. So there's a continual exchange of generation of electrons and holes with recombination, and the rates are equal and opposite. And so in an intrinsic semiconductor, we'd expect that the number of electrons just becomes Ni, and the number of holes becomes Ni. And indeed, that's what happens. So these generation and recombination processes balance each other out in the steady state. And if the only process is thermal, if the only processes are thermal processes, then we get the electron and hole concentration both equal to the intrinsic carrier concentration. If we're adding light, then that's a different story. So similar with generation, the major mechanisms of recombination are thermal mechanisms. So there's indirect thermal, or RG center recombination, and there's direct thermal, or band-to-band recombination. And these mechanisms are just exactly analogous to their generation counterparts. In direct thermal recombination, we've just got a free electron sitting up in the conduction band, and at some point it just spontaneously loses its energy, and it returns to annihilate a hole in the valence band, or to fill this unoccupied state. So this hole goes away, and the electron moves down to its new home in the valence band, where it can no longer conduct electricity. And in doing so, this electron emits a photon whose energy is just equal to approximately the band gap energy. And so this is exactly analogous to the mechanism for direct band-to-band generation. In indirect band-to-band recombination, we've got the same exact thing as before. So the band gap, which shouldn't have any states inside it, actually does have a few what are called trapped states. And so an electron can hop down into one of these states as an intermediate, and then meet a hole in its second hop. And in each hop, the electron releases a photon with energy equal to just the difference in the band. So we don't really know what those are at this point, but we know that it releases some amount of energy. And then the electron returns to the valence band, and it's no longer able to conduct electricity, and neither is the hole that it replaced. Okay, so those are all the major mechanisms of generation and recombination that we're going to cover, and our ultimate goal is to model them with differential equations. So ultimately, we want the continuity equation. We want an equation that describes electron concentration as a function of position and time, and hole concentration as a function of position and time. Because if we know these things and we know how they change, we know the currents involved, we know the voltages involved, we know everything there is to know about the semiconductor. And so in the next video, we're going to start modeling these processes with differential equations. And we're going to build up to the model that will finally let us start solving useful problems.